I'm going to present the work entitled Damage Evolution Predictions on Interlaminar Tensile Strength Specimens, which is a work done by my PhD student José Luis Guzmán, in collaboration with Professor Graciani. So the content of the work is, I will start with a brief introduction, and then I will give some ideas of the interlaminar tensile strength test, and I will focus on, mostly on the induced unfolding model that we would like to do. Finally, of course, I will end with some conclusions. So, what is the idea? We will work on curved panels made of composite materials, and we will focus on this test that is a standard test where the main idea is to measure the intralaminar failure when we have this kind of geometries. The failure is the usual failure is what we call classical unfolding, is the appearance of a delamination crack within the different plies of the composite. The point is that experiments show that when the plies are not aligned, we may find this kind of induced unfolding, which is nothing that we will first find a failure usually in 90-degree laminas, and then this failure will produce what we call an induced unfolding, which is nothing more than the delamination that occurred similar to the unfolding. But the main reason why we are interested in this topic is because the strength we found in this classical unfolding and the other induced unfolding are completely different. We are talking about 30 or 40% of difference. So if we found an induced unfolding, we will have a problem. So this is what we saw in experiments. What we found is that the usual unfolding usually appears around the middle of the specimen, but when we found induced unfolding, this failure is produced even on the lower part of the specimen. So those results were published by one of our former students, Juan González. What we are going to present in this research is a model including the delamination, but also the intralaminar failure. And of course, we're going to focus on the damage part that are produced in these kind of configurations. So for the delamination, although we could use any kind of model, we have focused on one model we've been using for many time, that is called the linear elastic radial interface model, which might be considered a simplification of the classical Poisson model, which basically means that we have only an elastic part, and once we get to a critical value, the spring or the continuous distribution of the spring just breaks. One of the main advantages of using this model is that it's very robust in terms of convergence. Another good advantage of this model is that the use of mixed mode is quite easy, because we can use the different stiffness for mode 1 and 2, and of course we can also relate the critical energy, also including the mode fracture. Recalling the interlaminar failure, we have used a tool that is already implemented in many codes. In this case, we are using Abacus, and this is the Hashing-Rotten model, which is a quite simple model, and which can be depicted in the following picture. So let's go with the model. As I told you, we are interested in this curved panel. The test that is usually done is a 4-point bending test. So the upper rolls are going down, these are fixed, and the laminate that we're interested in is a quasi-isotropic laminate, where we can find these 90-degree layers that will produce the induced unfolding. Regarding the geometries, those are usual parameters. Regarding the parameters of the model, we have used for the elastic properties, classical properties that we can find on the lab and also in the literature. Recalling the stress are also well-known properties, and maybe the most new ones are the ones that are needed for the degradation for the hashing model, and the ones for the interface failure, which can be done for our Levy model. Specifically, we can take into account these two values, which will rule the failure even on the interface or in the interlaminar part. So another interesting thing is that we are trying to make a simplification of the problem. So we're moving on a 2D problem. This means that although usually we can use anorthotropic properties or even transversal isotropic properties, we were forced to use anisotropic properties because if in 2D models, although we can move the angle, the only angle that can be allowed is the one within the plane. But as we want to model laminas that are out of plane, so we are forced to use the isotropic property. So this is just a standard. We rotate the axis of the material, and we obtain the axis of the anisotropic properties. So as an example, we can see here, for example, what are the properties that we obtain for the 0-degree lamina, which could be used directly with orthotropic material, or when we obtain the rotation for 90, 45, or minus 45. Some other interesting things is that if we want to model this kind of problem and we want to simplify most, we can use even a plane strain or plane stress problem. Both approaches might be correct depending on what we are looking for. If we want to focus on what happens in the middle of the specimen, so maybe the plane strain model would be the optimum. But if we are interested in what happens on the edges, so we can go with the plane stress. But another thing that we have to say is that the hashing model that includes the degradation in the interlaminar part is only able for plane stress problems. So this make that we have, although we have several models, those are limited depending on we are using plane strain or plane stress. So another thing that we have modeled is that in this middle part where the interlaminar failure is expected, we may use a pre-crack. So in this case, that we are assuming that the interlaminar failure already exists, or we can use a non-damaged part. So this means that we are not using this induced unfolding release. So these are recalling the plane strain model and recalling the plane stress. We may use the degradation model, so including pre-crack, we've got two options, and of course, when no damage is included, we also have these two options. Recalling what are we going to find when we will solve this kind of problems, we may find convergence problems, because we may find many possible paths for cracks. So we may find some behavior like this. When we start loading, we will reach a peak, and then suddenly 1, 2, or 3 interface cracks may appear. So we may find something what we call a snapback behavior, and the results may depend if we are applying a load control or a displacement control, so we may find different results. In fact, we are interested in the whole behavior of the snapback behavior, because if we are interested on the path of the cracks, the snapback behavior is an important thing. So what we have to do to get this path, this snapback path. So one of the things we found, based on a work of Emilio, who was there some minutes ago, we found that the problem is the control. Where we have to control? We usually control on the outer part, so we make a load or a displacement control. But those things or those controls will remain or will lay in these results. So what will be the variable of control? So thinking a little bit, we say we may find a variable that has to monotonical increase. It may be related to 1 or 2 nodes. In our case, this variable could be perfectly the opening of the lamination, for example, and we may also use not only one pair of nodes, but we can use many pair of nodes. So at the end, we found that the relative opening would be a good option for this variable of control, And of course, we may also found that not only the opening, but also the sliding would be interesting to be controlled. And of course, we may introduce this control in multiple interfaces. So, a little bit of detail about what we've been talking about. So, the main idea is that we want to control the jump displacement, both normal and tangential, of a pair of nodes. I said a pair, but it could be many pairs, okay? So, besides, we have a node or a group of nodes where we apply the external load. Then, what we have done is apply two auxiliary elements, which basically relates the variables in the pair of nodes where we are interested in, and the nodes where the load is applied. So we apply two auxiliary elements, just basically moving or applying these kind of equations, using a dummy node, which usually is located in the origin of the axis. So, how to include these equations? The easiest way is to use a feature that Abacus has that can be done directly on the IMP file, which could be the use of a user element using the matrix, the stiffness matrix. So directly we can play with this stiffness matrix as we want, so we can relate the variables as we want. So we will have two kinds of elements, of auxiliary elements. The first one, that is, for example, this, is relating the opening. For example, in this case, we are applying vertical displacement in node 1 and node 2. Let's recall what is node 1 and node 2. Remember, just in the practice, for example. We are relating this vertical displacement with a force. So at the end, let's recall also that this is not a real, an actual force. In fact, it's just the jump displacement, but allow us that in Abacus we can impose a C-load variable, which could be the jump displacement directly. So we will control that. And the other auxiliary element is the one that controls, again, this auxiliary element you see here with the applied load. For example, we can apply a load, or we may play also, we can apply directly a moment using the variable we want. For example, in this case, we are, sorry, there is a mistake here. It's not U, there is phi, I mean the rotation, because we are using the 6 degree of freedom. So we can play with that. So we can use the normal, tangential, rotation, or whatever we want. So what we obtain? For the plane strain models that no degradation can be included, we have two options, as I told you. The first one is a non-damage, where we can obtain this kind of behavior, the blue one, depending if it's a break or not. These curves are showing what we were looking for. If we focus on the outer parameters, it means the moment that we apply versus the rotation, we found the snapback behavior that we were talking about. But if we see if we plot the applied rotation versus the tip displacement, the opening, we see that this variable increases monotonically. That's why we are able to finally get all this snapback behavior. More, if we move to the plane strain, we are able to include the damage in the interlaminar damage. So in this case, we have both things. We have the damage within the laminas, the 90-degree laminas, and also to have this delamination. So we obtain some curves like this, where we can check some points, some interesting points, where, for example, the first point is the onset of degradation. It means that the interlaminar failure appears. We have then the 90% damage strength, then 100% damage strength, then the first delamination occurs, and finally more than 2 elements occur, and then you see that the loss of stiffness occurs, and we have this snapback behavior. So, as conclusions, we were able to model this induced unfolding damage mechanism, including both degradation and delamination, but for plane stress models. Remember that Abacus only allows for stress, for plane stress models. The control algorithm we have used is able to capture the complete history during damage propagation, which is something that we were looking for. And finally, some ongoing work that we are doing now. First, we will go to the 3D modeling using induced unfolding. where we can also want to research about the waviness of the different laminas, and of course the use of different criteria for the interface, like for example apply the couple criterion for the failure of interface. And of course we would like to make some numerical experimental correlations that the test campaigns that we already have. Just to conclude, thank you for your attention and acknowledge all the funding of this research.
Thank you very much. Any questions, please? Yes, please.
The concept of induced unfolding, you have first a transverse crack and then you have the debonding, is what you said.
Yes, terminations, yes.
Is that what you obtain in the numerical models as well?
Yes. So if we go back to the, here, using hashing, these 2 points are the degradation onset on the transfer line. Of course, we have used hashing, but we may use any other thing. If you see, we have a focus on the algorithm here, not on the degradation model, but I can say that now we have the capability to use anything we want.
Yes?
Maybe one rather technical question for the solution controls. Are you using some arc link or line search?
No, it's not necessary.
It's not necessary.
It's not necessary, yes, because we change the variable we control. We are not controlling the outer, but we are controlling just the opening.
Okay.
So that's the beauty, because we are not with all these convergence issues that may appear, because I show you just a simple example, but we have cases with we have 4 or even 5 delaminations and also some transverse crack, and the code is able to run with that.
Thank you. Maybe one more question and then we have to go to next.
So you are handling the crack opening at the interface?
At the interface, along the interface. And we can do it not only in one, but we can do it on several ones, and at the end the sum of everything makes that the work.
It was one question there, yes please.
Yes, I believe your defects are artificially introduced, yes?
Well, we have 2 options, in fact. In this case, we artificially introduced the first one. But in the second one, in this one, no. We started with no damage at all.
Okay, because in practice of manufacturing of composites, you may have some problems with short corners without any defect. So, what do you say about the meaning of the radius of curvature of this corner?
Well, that's a very nice question, because in fact in our lab we also found those things. Moreover, I would say that it would be a variable that is much more important, temperature. Because in this case I haven't taken into account all the residual stress because of temperature, and that's a key point. Yeah.
Thank you very much.